In this video, I'll be finding all the positive integer solutions to the equation a squared plus b squared equals c squared. And this is the well-known Pythagorean triples. So these are possible integer side lengths of a right angle triangle. Okay, so what I'll start by doing is first I will factor out the greatest common divisor of a, b, and c. So I'll let d equal the GCD of ABC. This means we can write a as d times some number a1, and b as d times some number b1, and c as some number dc1. So b is db1 and a is da1. And since we factored out the GCD of the numbers a1, b1, and c1, this must equal 1 because we've fully taken out the common factor, the greatest common factor. And now if we substitute these equations into the original equation, we'll get dA1 squared plus dB1 squared is equal to dC1 squared. And we divide out the d squared from both sides to get a1 squared plus b1 squared equals c1 squared. Okay, so now we just have to find all Pythagorean triples where the GCD of the three numbers is 1. Another thing is we can also prove a stronger condition, which is the GCD of any pair of these three numbers is equal to 1. So we can say they are pairwise co-prime. And to prove this, we can use contradiction. So if we assume, let's say assume a prime number p is a factor of a1 and b1. So this is the same as assuming their GCD is not 1. This means p must divide a1 squared plus b1 squared. And this is because if p divides a1, it divides a1 squared. And if p divides b1, it divides b1 squared. So p divides a1 squared plus b1 squared. And this means p divides c1 squared. And since p is a prime number, the only way for p to divide c1 squared is for p to also divide c1. But this is a contradiction because since the GCD of the three numbers combined is equal to 1, there are no prime numbers that divide all three of the variables. Okay, so this proves that GCD of a1 and b1 is equal to 1. And in fact, you can use a similar argument. So using a similar argument, you can prove GCD of b1 and c1 equals 1, and GCD of c1 a1 equals 1. And again, we can write a similar argument here to show these GCDs are 1. So if p divides b1 and p divides c1, it means p divides c1 squared minus b1 squared. And this means from here, p divides a1 squared. This only happens when p divides a1, and we get another contradiction. And finally, if p divides a1 and c1, it means p divides c1 squared minus a1 squared, which means p divides b1 squared. So p divides b1, and that's another contradiction. So this proves the numbers are all pairwise co-prime. Okay, so since a GCD of a1 and b1 is equal to 1, we have two cases. So the numbers can't both be even. So there's three cases. In fact, the first case is a1 even, b1 odd. Actually, I'll write wait. write A1 odd, B1. First case I'll do is A1 odd and B1 odd. Okay, so in this case, what we can see is A1 squared plus B1 squared. Now we can try to analyze this equation in modulo 4. So using modular arithmetic. So what we see is if we write a table of values of x squared mod 4, we have the following. So this is each of the values in mod 4. And this shows that an odd number squared, so an odd number is 1 or 3 mod 4. So when you square an odd number, it's 1 mod 4. And also there are no square numbers that are 2 mod 4. However, in this case, since A1 squared and B1 squared are odd, in mod 4 we have congruent to 1 plus 1, which is congruent to 2 mod 4. So that means C1 squared must be congruent to 2 mod 4. And this is impossible because there are no square numbers which are 2 mod 4. So there are no solutions in the first case. Now let's have a look at the second case where A1 is even, oh no, A1 is odd and B1 is even. Okay, in this case, we'll have C1 squared equals A1 squared plus B1 squared. Since A1 is odd, first the number A1 squared is odd, and since B1 is even, then B1 squared is even. So odd plus even gives us odd. And since C1 squared is odd, it means C1 is odd. Okay, now I can rewrite the equation as A1 squared equals C1 squared minus B1 squared. And this factorizes as difference of two squares. Okay, and now C1 minus B1 is equal to an odd number minus an even number, which is equal to an odd number. And C1 plus B1 is equal to an odd number plus an even number, which is equal to an odd number. Now we'll prove, the next thing we'll prove is that the greatest common divisor of these two numbers is equal to 1. And the reason this is good is if two co-prime numbers multiply to give a perfect square, this can only happen when the two numbers themselves are both perfect squares. And this can be seen using prime factorization. So in the prime factorization of A1 squared, all the exponents of the primes that divided must be even. And since if these two numbers turn out to be co-prime, it means in the prime factorization of the product, we can see the primes which make up each of these numbers are completely different. So the exponents of the prime factors in each of these numbers must be even, and it means both of these numbers must be perfect squares. So now we'll prove that GCD of C minus 1 and C plus 1 is C is equal to 1. And to do this, what I'll first do is you can add this number to this number. So this follows the Euclidean algorithm method. So you can add any multiple of this number to this number. So we have this thing, and this is equal to GCD of C1 minus B1 and 2C1. Remember, C1 minus B1 is odd, which means this factor of 2 doesn't contribute anything to the GCD, which means we can just remove the 2 in front of the C1. And this is equal to GCD of, now we can subtract C1 here. And this is equal to GCD of negative B1 C1. So the negative sign we can ignore. And the GCD of B1 and C1 from earlier is equal to 1. So we've proven the GCD of C1 minus B1 and C1 plus B1 is the same as the GCD of B1 and C1. So that's equal to 1. This means, again, from what we've discussed earlier, since the two numbers here are co-prime, it means they must be both square numbers that multiply to the square number a1 squared. So now we can write c1 minus b1 is equal to u squared, and c1 plus b1 is equal to v squared. Okay, and now what we can see is another thing is c1 plus b1 is clearly greater than c1 minus b1, which means v squared is greater than u squared. And since v and also we'll write okay, also we'll write u and v are going to be positive. So since u and v are positive, this is the same as saying v is greater than u. And also, since both of these numbers are odd, it means u squared and v squared are odd, so u, v are odd. Okay, now we can do c1 plus b1 plus c1 minus b1. This is equal to u squared plus v squared by adding the two equations. And this is also equal to 2c1, so we can find the value of c1, which is u squared plus v squared over 2. And by subtracting the two equations, we get v squared minus u squared. So 2b1 is equal to v squared minus u squared. So b1 is equal to v squared minus u squared divided by 2. And now a1 squared is equal to c1 minus b1, c1 plus b1. And this is equal to u squared v squared, or uv all squared. And now since a1, u, and v are positive, we can take the square root. So a1 must equal uv. Okay, another thing is since these two numbers c1 minus b1 and c1 plus b1 are co-prime, it means the GCD of u squared and v squared must be 1. So it means u and v don't share any prime factors in common, so it's the same as saying the GCD of u and v is equal to 1. Okay, so now we have the triple a1 b1 c1 is equal to, you have uv, v squared minus u squared over 2, and u squared plus v squared over 2. And remember, a, b, c, the original triple is equal to, we multiply everything by d. So we get duv, dv squared minus u squared over 2, and du squared plus v squared over 2. Okay, so this is in fact our final answer, a general expression for all the possible Pythagorean triples where, and this is in the case where a1 is odd and b1 is even. So this gives every single Pythagorean triple where a1 is odd and b1 is even. And the second case is actually quite similar. So last case is when a1 is even and b1 is odd. And in fact, using symmetry, it turns out it's almost the same as this case, except the expression for a and b is switched around. So we'll have d of v squared minus u squared over 2 and duv, and c is still the same. Okay, so our final answer, by combining these two cases, final answer is, so we have two possible classes of triples that work. So we have this is the first triple that works, and the second triple is where a and b are switched around. And the conditions that are needed on u and v are So D has to just be a positive integer. V must be greater than U, and V and U are positive integers. V and U are both have to be odd. And also the GCD of U and V are 1. So these are the conditions on U and V that give every single Pythagorean triple. Okay, so that is all I have for this video, finding all Pythagorean triples. Hope you enjoyed the video. Thanks for watching, and I'll see you next time.